computer, I guess. Okay, I think we're recording. So let's begin then. So I'll read the question. So suppose you're a recently vetted materials engineer into the German Air Force who is tasked with analyzing a simplified model of the collision between the two Eurofighter Typhoons. Let me get the pen out. Okay. I can't switch screens. All right. The senior materials engineer provides you with the stress strain curve as shown below for the continuous and aligned carbon fiber reinforced epoxy composite that was used to construct the airframe. During impact, the crashing force, F crash, was not perfectly aligned with the orientation of the carbon fibers as shown in the schematic down below. Therefore, both longitudinal and transverse forces were applied onto the composite before the Typhoons exploded. Given that the fiber matrix interfacial bonding is very strong and the deformation was totally elastic before the explosion, determine the magnitude and direction of the crashing force, F crash, that was exerted onto the airframe at the instant of impact, causing a longitudinal and transverse strain of 0.002. Okay, does everybody understand the problem? First off and foremost. Yes? Maybe. Kind of. Determine F crash. Okay, F crash is this guy right here. See this? As soon as that plane hit the other one, there was a crashing force exerted onto the airframe and that airframe. Are all these curves different composites? No, they are all the same composite. So let me see if I can just highlight it. So this one right here is your, that's really thick. Okay, so this one here is your carbon fiber. Okay, that's the stress strain curve for your carbon fiber, the reinforcement alone. The one down here is your epoxy resin by itself. And then these two here are your composites. They're the exact same composite. The only difference is one of them is experiencing a longitudinal force and the other one's experiencing a transverse force. Is that clear? So yes, at the end, you will be solving for the resultant force. That is correct. Okay, so we're good. We understand the problem. There's one thing that I want to point out before we move on. You'll notice that this schematic did change. Before it used to look something like this, right? You all saw that? What I had drawn previously is not wrong. It just may be confusing because I did get a bunch of emails asking why it's extending past this point right here. Don't get confused. The point that I have a big X on right here, that is the onset of failure. That's not where the composite fails. Okay? That's the onset of failure. All right? With that being said, I think we can move on, unless there are any questions about that. What does the onset of failure mean? So the way the textbook defines the onset of failure is when the fibers fail. Okay? So in the theoretical aspect, all your fibers are perfectly aligned and they're all experiencing the exact same stress at the exact same time. So in this case, if it's longitudinal, then they're all experiencing the exact same elongation, which means the exact same strain. However, we know we can never do that. There's never a perfectly aligned composite. So you may have the majority of them aligned, but there are some still in opposite directions. So it may actually increase past this point or significantly before this point. But in a theoretical aspect, we define this point here as the onset of failure. Okay? All right, so I hope that's clear. Let's move on. So determine the volume fraction of the carbon fiber within the composite. Does anybody have an idea on how we're going to do this given the information upstairs here? Anybody? calculates its radius. No. We're looking for VF, right? VF. Has she taught us this? Yes. No. Close. So what's this equation? Right? Plus what? You never did this equation? You must have done this equation. So what this equation allows you to find, stress star CL is this one right here. Right? That's this. That's your strength in your composite. Okay? Yeah, so this is one of the basic equations for composites. So it maybe she hasn't covered it yet, but you will cover it and you will see it on your midterm. So know this equation. It's very fundamental. It's just allowing you to solve for the transverse stress generated. Sorry, it's allowing you to solve for the stress generated by the longitudinal load. Okay, on the composite. So the maximum strength of your composite, when loaded longitudinally, it'll give you this value. Okay. Right? Okay. What is this one? What is sigma prime m? Do we know what sigma prime m is? Okay, I'm going to answer Kyle's question first. If you look, we are far past the linear elastic region, right? Therefore, we can't use Hooke's law. So if you just want to do stress divided like equals force over area, you don't have any force, right? You have the area, but you don't have any force. So you're going to solve for force, and then what? You're looking for the volume fraction of the fibers. Okay? Okay, so I think all of you are answering my question. So stress where the fibers fail, it's stress in the matrix at fiber failure. So you're mostly correct. So at that point, the fibers fail here. So we're going to go down, and this is the point right here, which is our stress prime M. Okay? Are we good with that? Yes? It's a strength in the matrix at fiber failure. Okay? And then the last one is this one right here. What's this one? Sigma star. That's just the, yes, correct. Okay? So once you know what all the variables are, this question is very, very straightforward, right? Okay. So let's assume that we learned all the variables. We can plug in our values now, right? So 2,500 megapascals is equal to 25 megapascals 1 minus VF plus 4,150 VF. Okay? Are we good up until there? So now only thing we're solving for is VF, right? Can you plug that in your calculator and let me know what you get for VF? .6, that is correct. So our volume fraction of our fibers is equal to 0.6. Yes, everybody understands? 4,150 is the stress at which the fibers fracture. No, it's the ultimate tensile or the greatest strength of the fibers. Okay? In this case, and most likely always, it'll be the point of failure. All right? Okay. Does everybody understand how to do this? Are all these sigmas are at the fiber failure line, right? Yes. Yes. Okay. Why do we determine the volume fraction from the point of failure? That's a good question. We're not necessarily doing that in the way you said it. We just need this data to be able to determine that. Like if there's another way on here that you see that you can determine the volume fraction of the fibers, go ahead and do so. But I don't think I gave you enough data in any other aspect to determine it. Can I ask a question through mic? Yeah. Feel free to turn on your mics, no problem.
Hi. I have a question. So here we decided to go with the 0.6 strain, the strain at 0.6 because that's where carbon fiber fails. But like previously, we only had matrix and one reinforcement, but here we have one matrix and two reinforcements. So I was wondering why we don't pick like 0.9, which is where the carbon fiber epoxy composite fails. I'm a little confused.
Are we looking at the same problem?
Because there's
sorry, I don't know where'd you get 0.6 from?
like on the strain line.
On the strain line, 0.6. Oh, you're looking at a strain of 0.6.
Yes.
No.
So we got the stress of the matrix at that point, and we got the stress of the composite at that point, and then we got the stress of the carbon fiber at that point.
Okay. So no, I see why you're confused. So what we did is, first off, there's only one reinforcement. It's only carbon fiber. Okay. The greens are the exact same composite. The only difference is one's being loaded longitudinal and one's being loaded transverse. Okay. So it's the same composite, same reinforcement, same matrix. Now, what we do is the way that this equation is defined, it's using the strength CL, which in the textbook is shown to be there. So the onset of failure is at the point where the fibers fail. So we're taking stress star or sigma star at the point of the carbon fiber failure, sigma star CL at the onset of failure of the composite in the longitudinal direction, and then sigma M prime is the point on the matrix stress strain curve at which the fibers fail. So
okay.
not necessarily looking at the 0.6 value, it's looking at where the carbon fiber fails.
Okay.
Okay.
But just as a general question, will you always have like one curve for the reinforcement, or can you have like two different types of reinforcements?
You could. That's called a hybrid composite. There's no way that we would test you on that.
Okay. Okay, cool.
Because there's no way to determine what's actually happening inside there based off of these equations anyways. So you would always have only one reinforcement. Okay?
Mm-hmm.
Okay. I hope I answered your question. I just didn't make you more confused or went around your question. Okay. Is there anything else or anybody else? Yes, the matrix is the epoxy resin. Why do we only take the longitudinal direction, not failing the transverse? Okay, so this equation only holds for the longitudinal loading. Okay? This one, the one we just used to calculate the volume fraction. Okay? That's why it's sigma star CL and not sigma star C. Okay? We're good to move on now? Yes? Okay, part B. Calculate the modulus of elasticity in the longitudinal direction for the carbon fiber reinforced epoxy composite. So how are we going to calculate the modulus of elasticity? Do we have any suggestions? There is a formula. There is a formula. Yes, that is the formula that I want to use. So we're going to say that the modulus of elasticity for the composite in the longitudinal direction is equal to EF VF plus EM VM. Okay, we can also say that that's equal to EF VF plus EM 1 minus VF. Right? Are we good? So substituting all of our values. Do you want me to write down the values, or are you okay to find them from the table, from the graph? Write down the values? Okay, let's write down the values. Okay, so the modulus of the fibers is given as 398.4. So 398.4 times 10 to the 9 pascals times VF, which is 0.6, plus EM, which is 2.4 times 10 to the 9 pascals. And again, that's times 1 minus 0.6. Okay? Plug that into your calculator and you're going to get what? Yes, let me write down the answer and then you can ask your question, okay? Do we have an answer? No? How about 240 gigapascals? Yes, correct. What did I call this equation again? I called this the rule of mixture equation. Okay, somebody had a question that they wanted to turn on their mic. Please go ahead.
Hi, can you hear me?
Mm-hmm.
The question I had was for the first part, like determine the volume fraction.
Yep.
Did we only use longitudinal because like the longitudinal formula because we don't have one for transverse?
Yes, that is absolutely correct.
But okay, so every time they ask for volume fraction, it's always the longitudinal.
Well, you can determine volume fraction in other ways too, right? Like you can use this rule of mixture equation. Say that you were given the modulus of the composite in the longitudinal modulus of the composite, you can find VF, right? So VF's like a thing that you can solve for in many different ways. In this case, this was the only way that we could solve for it.
Okay.
But this equation is originally used to calculate stress star CL.
Okay, thank you.
Okay, no problem.
So can you ever calculate it or in the transverse direction, or all the equations that we know of in the longitudinal direction?
There is no way in this course to calculate the transverse strength. Okay.
So then why would it be given on a graph? Like
Why is it given?
yes.
Because you may need it, I think, later on. I don't remember every single question off the top of my head, but I think you may need it. And if you don't, I just put it in there just to have it, just to confuse people, I think. Either or. Okay.
So you wouldn't need it for calculation purposes, right? Just
so far, no, we didn't need it. Let me look at the rest of the questions just to see if we will need it. I don't think we will. No, we never need it. So I threw it in there just to, I guess, confuse people.
okay, thank you.
Okay, so it was just a trick, I guess. All right. Okay. So we're good up until this point, right? Nobody's confused? Okay, I hope so. Oh, I hear a mic. No? Okay. We'll go to the next one. Next question, if it allows me to do so. Okay. Determine the longitudinal force that was induced onto the airframe during impact before the explosion. How are we going to do this? Anybody have an idea? Think to what we know. Oh, somebody's on vacation. I like that. I wouldn't be at vacation. FC equals FM plus FF. No, not necessarily, because we don't have FM or FF. Sigma CL is equal to force CL divided by area CL. Yes, that is a good way to do it. Do we have area? Yes, area is given. I do want to mention something though. The reason we can't use that equation is why. Somebody's mic's on, by the way. I don't know if it's intentional or not. Not linear. So the problem said what? The force caused a totally blank deformation. Elastic, yes. So we can't use the equation you just said because why? Look at what you wrote. You wrote sigma CL. What is sigma CL? It's any, no, it's not critical. It's any strength on the composite in the longitudinal direction, right? But the only one we have is sigma star CL, which is not in the elastic area or elastic region. So that's not the stress we're looking for. Okay? So what we can say is, because we know it's totally elastic, we can use Hooke's law. We can say the Young's modulus of the composite in the longitudinal direction, let me keep, right, is equal to stress over strain, and this is in the composite longitudinal, right? But we don't have the strength of the composite in the longitudinal direction for this specific force, right? So we're going to do that manipulation again. We can say that the force of the composite in the longitudinal direction divided by the area of the composite times the strain of the composite is equal to the Young's modulus of the composite in the longitudinal direction. Did everybody see what I did, or did I go too fast? We don't have this, right? So we had to replace it with force over area, which is what we're looking for anyways. Okay? All right. I'm hoping everybody understood what I did. So now all we have to do is isolate for our force. So our force of our composite loaded in the longitudinal direction is equal to our Young's modulus of the composite in the longitudinal direction multiplied by our area of the composite multiplied by our strain. Now, what strain is this? What strain value are we going to take? Strain of the composite. Okay, what else? So that is correct. This is strain C. But what do we know about longitudinal loading? If these are all our fibers and we're loading in the longitudinal direction, what do we know about the strain of the composite? It's equal to the strain on the fibers. It's equal to strain on the matrix, right? Because this is a iso strain condition, right? So because they're all equal, we can say that this value is equal to 0.002 from the problem, right?
Could you just repeat what isostrain means again? Is that just when the fibers are aligned in the same direction that the force is applied?
Yes, that is correct. So when it's loaded in the same direction of the fibers, then we have an isostrain condition, meaning that the strain exerted onto the composite is equal to that of the matrix, is equal to that of the fibers.
Okay. And does it matter whether the fibers are continuous or whether they're the smaller one?
I'm
Right.
going to say yes, because that's the terminology your textbook uses.
So is this one for when they're like the long type or the short type, right?
The long type.
Okay.
Okay.
Hello.
Yes, go ahead.
Okay, my question is just for when you're doing this calculation, you said that we can't use sigma CL, or well, we don't have sigma CL.
Yes.
Can you scroll up to the graph for a second?
Yes, I can do so. Okay.
So that value there, sigma star CL, that is the stress at which the composite, the onset of like failure in the composite, right?
Yes.
So we can't use that in the in that problem per se, because that's where plastic deformation starts. So we need something
Yes.
before that, but we don't know anything before that.
Yes, that is absolutely correct.
Okay. So
Okay.
when we're doing these questions, like let's say on the test or the midterm, like there is something similar, we need to like beware if it's plastic versus elastic, because if it's elastic, then we can use those formulas like stress is equal to force over area. But if it's not, then we can't use those, right? We should be using the other ones, like the other composite ones.
Yes. So stress is equal to force over area. You can use regardless of if you're in the elastic or plastic region.
Oh, okay.
But in this case, if you were to use force over area, you would get the force at the onset of failure, not the force governed by the initial impact.
Oh, okay.
Okay.
Oh, we should just be careful then.
Yes, you should be very careful.
Okay.
Okay.
Thank you.
No problem. So there was something else that I was going to say. So we're here. So I actually told you in the problem that the strain in the longitudinal and transverse is 0.002. So you didn't actually need to know what I explained here, the isostrain condition, but let's say that it was not given that clearly in the problem, then you would need to know about the isostrain condition. Okay, because on the 2019 midterm, she actually didn't specify. She wanted you to know that there is an isostrain condition, meaning that the strain on the fibers was the strain on the composite. Okay, but in this problem, it was very clear. It was stated. All right. So problem D, if I can get my pencil working again. Problem D says, compute the magnitude of the load carried by each of the fiber and matrix phases governed by the longitudinal force. So how are we going to do this?
Sorry, but for the question before, what's the final answer?
Oh, did we not actually plug it in?
No, you never solved it.
My fault. I'm shooting the gun a little bit. Okay, does anybody want to plug it in? Or I can just, do you want me to write the numbers? I can write the numbers.
Yes,
please.
please.
I'll write the numbers, okay. So this was, we calculated as 240 times 10 to the 9 pascals. The area was 1 times 10 to the minus 4, I think, meters squared. And the strain was 0.002. Okay, so your F on the force of the composite in the longitudinal direction is equal to, let me see what I got. Okay, anybody want to give me their answer first before I write mine? No? Okay, I got 48,000 newtons. The strain on the solution sheet was 0.9. Did it change? Yes. So that's what I was saying. I had to update the problem because I didn't give you the strain. So when I initially solved it, I used the incorrect value, but that was my fault. Okay. Yeah, I should have given you 0.002 to begin with. All right. Okay. Can we move on now? We okay? Yes? All right. Compute the magnitude of the load carried by each of the fiber and matrix phases governed by the longitudinal force. How do we do this? Somebody mentioned the equation earlier, actually. Force of the composite is equal to force of the matrix plus force of the fibers. Okay. Yes, we can use FCL for sure, because again, we want it governed by the longitudinal force. So we can say that this is FCL. Did everybody follow me there? Okay. So we can say that 48,000 newtons is equal to Fm plus Ff, or we can say that Ff is equal to 4,800 newtons minus Fm. That'll be equation number 1. Yeah, so what we're solving for is the matrix and fiber, the load carried by the matrix and the fiber for the longitudinal composite, the one that's loaded in the longitudinal direction. Okay? Why can't you do force the composite equals strain times modulus times area times volume fraction? Why can't you do strain times modulus times area times volume fraction? Ooh, that's a good question. Substitute those values in and let me know what you get. Because this might be one of those scenarios where you can have 2 possible solutions and they'll be slightly different. So plug in the values, I'm curious. But in this case, you would need, the way I solved it, you need 2 equations, 2 unknowns, because that's the way your textbook solved it. Well, not this problem, but a similar problem. Can we use the same equation if we were asked to calculate FC in the transverse? Yes, absolutely. You can use the same equation. But in this case, we're dealing with the longitudinal force. Okay. Okay, so we need one more equation because right now we have 2 unknowns. So what's going to be our next equation? The ratio, yes, absolutely. So FF divided by FM is equal to EF VF divided by, oh, that's supposed to be EM VM, which is equal to EF VF divided by EM 1 minus VF. Okay, so if we simplify this, I'm running out of room here. We will get this at the end. Let me just write it. So we'll get F C L is equal to FF plus, hold on. It's gonna be a constant, 249 FM. That's what I was trying to write. It took me a long time to get there, but that's what I was trying to write. That's equation number 2. Did everybody get that? Where did I get this equation from? That's another just rule of mixture equation. Okay, I got fibers 47,808 using the other equation. Okay, and the 5. Okay. Then yes, you got the exact same answer that I did. So yes, I guess there are 2 ways you can do this. And this tend to yield to the same value. So I'm really impressed. If somebody wants to take a picture of their answer and send it to me, I'll add it to the solutions as like an alternative solution. Okay. Okay, so let's continue. So right now we have two equations, two unknowns. We know how to do that, right? Substitute one into the other and solve. I would do it, I'm just running out of room. So at the end, we're going to get FF is equal to 47,808 newtons. And FM is equal to 192 newtons. Okay? That's our answer. Is everybody okay with that? Two equations, two unknowns, make them equal and solve, and then substitute back. Okay, okay. So are these composites equations only applicable to stage one? I was waiting for this question. So no, these ones aren't. Okay, but anytime you use an equation that we're using earlier for here, when we use Hooke's law, then yes, they have to be within the linear elastic region. But the equation we use to solve part A, or this equation here, part D, they don't have to be. In the tutorial video, we did something like FF divided by F equals 0.9 divided by 0.2 when calculating the ratio for the tutorial question. Why don't we use the same ratio equation here? Because we're not given, oh, so you're saying that's not a standard ratio. The problem told you that 90% of the load is carried by the fibers. So we created that ratio based off of what was given in the problem. That's not standard. Okay? Yeah, no, that's not a thing. That was for that specific problem. All right. Okay. Are we good with this? Everything up till part D?
Hello.
Yes.
So what Michael wrote in the chat about his other way of doing the question, that's using like the engineering stress and strain formulas, right? Like sigma is equal to F over A, and then he just replaced A with the area of the composite times the volume fraction of the composite. That would just be the other method, because that's what I originally thought too.
To be honest, I can't really see it.
I know.
He got the same value, so he did something right. That's why I asked for the solution. But I'm not sure what stress value he plugged in.
Yeah, I was gonna ask that. Or Michael,
Maybe he actually did force the area. I don't know. Is Michael there?
I think so.
Does he want to speak?
Maybe he'll type it.
Okay.
It's early in the morning.
I know it is very early.
That you guys want to know?
Oh,
Hey,
what
what
value of stress did you plug
What
in?
stress did you plug in? Yeah.
I broke stress into modulus times strain.
Oh,
Yes. Okay. So then, yes, his method is absolutely correct.
okay, that makes sense. Because if he didn't do that and he just chose some random, or like the tensile or the failure, the sigma star one, it probably wouldn't have worked, right?
Yes, I doubt it would have worked.
Okay, sounds good to me. Thank you.
No problem.
Now, can I ask you a question?
Yes, go ahead.
So, like, you said that you can use part D's equation, force fibers over force modulus equals that stuff
Yes.
in stage 1 and 2.
Yes, that's correct. Because we're
I'm
not
confused. Why
Pardon? Sorry, I cut you off.
I'm confused why you can use it in stage 2, because doesn't that involve Young's modulus, which means you're using like Hooke's law?
Well, Young's modulus is a material property, correct?
Yeah.
Once you've calculated Young's modulus, it's set in stone for that material. So we can actually use it as a ratio in this case, using the rule of mixture to determine other properties. So the properties that we're determining here are all relative.
Isn't Young's modulus only a material property in the linear elastic region?
No, the only way you can calculate it is using the stress and strain in the linear elastic region.
So you said this equation and the equation we use to solve part A are the only two equations applicable in stage 2?
Any rule of mixture equation and the equation in stage 1. Yes. So this equation could be used for different things, right? Like we could say, What other equation did I use? Did I use anything else? What did I use for B? Let me see what I used for B. Okay, so this is another rule of mixture equation. See equation B, the one I used in part B, that can also be used for anywhere. Okay?
So like really the only ones that are limited to stage 1 are the ones that have Young's modulus equals stress over strain in
Yes.
both of them.
Yes, that's correct.
So like my methods only works for stage 1 because I substitute strain for modulus times, or substitute stress for modulus times strain.
Yes, so your method would actually work in both cases as well, but you would have to use the stress value, you couldn't substitute E over epsilon.
Like in this case, you're allowed to because it's the linear elastic region, right?
Yes, absolutely.
Okay, thanks.
Sorry, I hope I answered your question. It was really hard to do in the email, so I'm glad you asked now.
I have a question.
Yes.
So I'm a little bit confused about like all the equations that we're throwing around here since we were just introduced to them.
Yeah.
So I don't know if we have time for it, but I was wondering if you could do like a little rundown of all the different equations we can use when we're doing composite calculations and like when to use them.
So there's a beautiful table.
Oh my God.
Right from the textbook, we can go through it very quickly. So the first one here is a rule of mixture. Okay, so this is going to give you your upper bound. So this is, if you have this sort of curve, your upper bound looks like this and your lower bound looks like that, right? They're both going to end up at the same point. So the upper bound is going to give you the maximum values and the lower bound is going to give you your minimum values. Okay, generally we'll always use the upper bound unless otherwise stated. This one right here is the one we also used. This is for your composite in the longitudinal direction. Okay, again, this is a rule of mixture equation. This is the one for the transverse direction. This is the equation we used in part A, which is the longitudinal tensile strength for a continuous and aligned fiber. So this strength star CL is the ultimate, or at the point of onset of failure. And then this one here is for discontinuous. And then this one here is for discontinuous as well, depending on the length versus the critical length. Okay.
Okay. So for the first one, you mentioned that we always take the upper bound. Why is that? I think you said it, but I missed it.
Just because that when we look at this equation down here, they're essentially the same. So when we're dealing with composites, we generally just use the volume fraction times whatever property we're looking for, plus the other property times its volume fraction, versus having to go to the lower bound, which is just going to give you a lower value.
Okay.
Okay. So I would say these are the equations down here, are the ones that you would need to know. Oh, and this one. Okay.
What's that one? I haven't seen that one.
This is the critical length equation. So the critical length is going to be useful to determine which discontinuous formula you're going to use. Okay.
Oh, okay.
Let me erase most of this. I'm assuming Professor Zari is going to cover all of this. But just so we're all on the same page for now, I think that was a good idea to go through the formulas. So thank you for that.
Thank you.
No problem.
Don't go. Oh,
Don't.
don't.
Okay.
Yeah.
I'm back.
Sorry. My question is just about the critical fiber length formula or
Yes.
equation. Yeah. Okay. Tau C. She mentioned what that was. It was like the minimum of two things. Can you explain briefly what that is again? Like, I just didn't understand what she was talking about it.
Your
I
stress.
was like, what? Yeah, like like how, if you were given, like, would it just say like the shear stress, or what would be given something else to calculate that?
So she gave you a formula to calculate the shear stress?
No, she just said it was, hold on, give me 1 second.
Yeah, no problem.
She said,
Or show me what you're looking at.
yeah, so she gave us that formula and she said tau is the minimum of the fiber matrix bond strength and the matrix shear strength. So
Yes. So whichever one is lower, that's the one you're going to put in.
oh, okay.
Of
So
those two values.
so between those, like, let's say we were given those two and one was smaller than the other, we would just pick the smaller one.
Yes, absolutely. Actually, that's a really good test question, to be honest, because that just checks your understanding if you know which one to choose.
Oh,
Okay.
well, now I'm happy that I know because I didn't know like 5 minutes ago. So thank
Good
you.
question.
Oh, Mohammed said, what was the question again? So
You can go ahead and explain to him so I can test your
I'll say it again. So
Okay.
I don't want to miss out. I just asked, when she gave this formula in the lecture, she said that tau C was the minimum, and then she put like in brackets of the fiber matrix bond strength or the matrix shear strength. So I didn't know what she meant by that, like why there's two different quantities. So Nella just said that let's say you're given both of those in a problem, then you would pick which one was lower. So either the fiber matrix bond strength or the matrix shear strength. So I guess if we were told both of those, then you just pick the smaller one because it's the minimum.
Absolutely. Okay.
I have a quick question
Yes.
on the formulas as well. Like all of these can be used regardless of the stage, right?
Yes. These ones can. Yes.
Only the Hooke's law is used in stage 1, right?
That is absolutely correct.
Okay.
Okay. So I hope Michael was listening because that'll answer his problem too, or his question. Okay. Are we good? Can I move on? Anybody else want to speak up? No? Okay, let's move on to the transverse direction. Since we're okay with the longitudinal. Let me change this. Get out of green. Okay, calculate the modulus of elasticity in the transverse direction for the carbon fiber reinforced epoxy composite. So now that we did the longitudinal, how can we do this? No, not lower bound equation. The other equation.
The other one, you just said it. It was just there on the sheet. You could go back to the sheet and I'll tell you which one.
Okay.
I think. Maybe I'm wrong.
Which one?
That one. Modulus of elasticity for continuous and aligned in the transverse direction. That one.
Discontinuous
The one.
and aligned
5. Is
transverse direction. Yes.
that wrong?
Yes, you can.
Okay.
Absolutely. Okay. Okay.
Okay.
Let's copy that. I actually don't think that that's what I did, to be honest.
Oh,
Oh, no, I did do that. Okay.
I was like, how did you do it
Yes,
then?
yes, yes. I thought I messed up the solution, but no. Okay. I did what I was supposed to do. All right. So let's use that equation. Where'd it go? Okay. So what's the equation? E C T is equal to?
I don't know. It was just on the
You don't know, it was just there. Okay. EF divided by VM plus VF, right? Or EF divided by EF 1 minus VF plus VF. Okay? We're good so far? I'm assuming everybody wants me to plug in the values, so I will do so anyways. So our modulus for the matrix, I believe, was 2.4 times 10 to the 9 pascals. And the modulus of the fibers was 398.4 times 10 to the 9 pascals, divided by the modulus of the fibers, which is 3.98 times 10 to the 9 pascals, 1 minus 0.6 plus 2.4 times 10 to the 9 pascals times 0.6. Okay? Are we good, or did I go too fast plugging in the values? We're okay? Okay, so what's our final answer then? Substitute? Sorry, crunch. Plug in your calculator and crunch. Crickets. Okay, how about 5.95 gigapascals? Did everybody get that? Just check your answers. Is everybody still there? Can everybody hear me? It got real quiet all of a sudden.
Yeah, we can hear you.
Yes.
Okay, I was like, where did everybody go?
Nello, it takes us a second to plug it in.
Okay, okay.
Give us like a
Go
minute.
there.
Also, I have a question. This isn't really related to this part of the question, but I have to get to a tutorial, so I want to ask it before I have to leave.
Okay.
In the beginning of the question, we were told like the percentage of the composite and the percentage of the carbon fiber and the percentage of the fiber reinforced. Like in the very beginning in the problem statement.
Yes, we were. Oh, you're talking about these percentages here?
It was like, oh, this is 82%, the other 70%. Yeah, so I was wondering if that information is important because that kind of, yes, because when I first saw them, my first thought was, oh, they're related.
You're cutting out.
Oh, hello?
Hello? Okay, I can hear you again.
Okay. So I was just saying that when I first saw them, my first thought was that they might be related to the volume fractions of the material,
Okay.
but it's not. I mean, it doesn't add up to, like the composite and the fiber don't add up to 100, so obviously not. But like, is that?
That was just like a for your information sort of thing. Like aircrafts are made by 82% composite materials and 70% of them are carbon fiber and 12 are glass fiber reinforced.
Okay, but if like the composite, if the question was totally different and we were given this percentages and it was like, oh, it's 60% composite and it's 40% fiber, then those would be the volume fraction of the composite and the fiber, right?
Absolutely, I would agree to that.
Okay, okay.
Okay, going back. So everybody got 5.95. I didn't plug it in wrong because I tend to have a habit of doing that. So yes.
Oh, it's right. It's right. It's right.
Right? Okay. So now part F, determine the transverse force FCT, if I can get there, that was induced onto the airframe during impact before the explosion. So what are we going to do here? We did it already for the longitudinal. This one, part C. We're going to do the same thing. So the modulus of the composite, the transverse direction is equal to strength of the composite divided by the strain on the composite. Further, force of the composite in the transverse direction is divided by the area of the composite times the strain in the transverse direction. Okay? Substituting or rearranging, FCT is equal to ECT times A times strain T. Okay? Can you explain real quick why the strain is not 0.4 where it's the 0.2 in the new question? Yes, 0.002 is given in the new question. Okay? Yeah. That's the only reason why these equations work, is because I give you that value. If I didn't give you that value, none of these equations would work. So I apologize for the first upload. Okay? All right, so let me plug in the values. So we get 5.95 times 10 to the 9 pascals times the area, which is 1 times 10 to the minus 4 meters squared. And then our strain is 0.002. Final answer would be, I don't know what's happening out there. I'll wait as everybody plugs it in. Yes, area is the same. The composite area is the same, regardless. Okay, no problem. Yes, I like that answer. 1190 is good. I'll wait for a couple others to confirm, and then we can move on to the trivial part of the problem, which is just Pythagoras, I think it's called.
Just
Yeah.
a quick question. We could use force over area, sort of the elastic modulus, because we're working from E, like from Young's modulus. Is that why we could use that formula in this question?
Sorry, can you just say that again? You got cut out at the beginning.
Yeah, sure. So like we're using based off E, like
Okay.
the Young's modulus, because it's a material property, so we don't have to be worried about whether it's elastic or not. Like, is that
So yes, it's a material property, but in this case, we need to, because we're using it with stress over strain, we need to, that's Hooke's law. So we have to be within the linear elastic region, right? So the problem said that at this strain value of 0.002, the failure is completely elastic. Sorry, the force gate was completely elastic. So we can use it.
Oh, okay. Sorry, I missed that. Thank you.
Yeah, no problem. Okay.
Might be a really dumb question, but so in part D, how we used the force of the composite in the longitude direction equals Fm plus Ff. Does that not apply? It's like in part D, the first one. Does that apply in the transverse direction as well, or?
Yes, absolutely. I actually could have added another question saying determine the magnitude of the load and on the fiber and matrix in the transverse direction as well.
Okay, and also if we were given matrix and fiber, then we could have just done that to find the transverse, right?
Yes.
And the forces will be different though than what they are in part D though, because those are all, like for example, a force fibers, that's in the longitude direction, that's specific.
Yes,
Okay,
absolutely correct. That's absolutely correct. Okay. Did everybody get 1190? Or
No.
is it Samantha? No, somebody didn't. Okay, who didn't?
Oh, it's still me. It's still Samantha.
You put 1190.
My question is just, I think kind of going off the other question, I just want to confirm for part F, we are allowed to, I can't remember now, it's so much information, but so we're allowed to use these formulas anywhere, you said, right? Like these F over A and strain, like, no, this is the linear elastic one,
Yes.
right?
Yes.
Okay,
Yes.
that's why we could use these.
Yes, you
Yeah.
could use it only because the strain is in the elastic region.
Okay, and how would we know that again? Oh, I guess they told us, right?
Yeah, the problem said the
Okay.
force generated an impact that was completely elastic.
Okay.
Okay. No
So
problem.
other ones that is anywhere, like those Young's modulus ones.
The other ones you can use anywhere, correct.
Okay, thank you.
No problem. Are there any other questions up to this point? Okay, I'll take that as a no. Now we'll go back to grade 12 vectors. We can just add up forces. Okay. So if this is F crash, and that's what we're looking for, we know that we have a transverse, which is FCT, and we have this, which is FCL. And we know that this one is equal to 48,000 newtons, and this one's equal to 1190. How do we find F crash? Is equal to somebody say it. Who's the man's? Whose law is it?
Pythagoras.
There we go. Thank
It's
you.
a second.
Okay. Squared plus 1190 squared, right? Yes, I like that final answer. So we can say that F crash is equal to 48,015 newtons. Okay. Last part of the problem wants us to determine the angle. I don't know if I labeled it alpha or theta. I'm going to go with alpha just for now. So how do we get alpha? Alpha is equal to tan inverse of FCL divided by FCT. Do we need the angle 2? Yes, we do need the angle 2. So by plugging in those values, we're going to get 88.6 degrees. So we can say finally that our F crash is equal to 48,015 newtons at an angle of 88 degrees, 88.6 degrees. Okay. I went a little fast there because there's nothing really tricky here. Hopefully we're all able to do that. I'll give you a couple minutes. MIE 100 crossover with APS 110. I have no idea what those are, so yeah, I would say grade 11 physics. It goes that deep.
Is it possible for after this question we go to like one of the tutorial of the video questions?
Sure, absolutely. For composites?
Yeah.
Yep.
I just want to know mostly about the stiffness equations. That's all.
Okay.
Excuse me?
We also have magnetic materials to do today as well as midterm review. So I'll let you all decide what you prefer.
Okay, yeah, then it's fine. It's fine. I can just write it.
No, we can do that too. It'll take 2 seconds, right?
Yeah, just it's really quick.
Yeah, that's fine.
Excuse me?
Yes.
Yeah, just had a question in the beginning for the short answer. I was wondering if we can go back.
Yes, no problem.
Thank you.
Let's go to short answer. Wow, this was a long quiz. Okay. Yes.
Yeah, it's part D.
Yep.
Yeah, when it tells you what is the fatigue strength, like I tried to answer, but I didn't get the exact answers. Like, is it like just by estimations, or like how can we get the most exact answer?
Okay. Can you tell me what your answers were?
Like I got for A, I got 320 megapascals. For B, I got 130 megapascals.
Hold on. Let me just open mine so I don't give you wrong answers. Okay, so you got, sorry, what? 3?
For A, I got 320 megapascals.
Okay.
And then for B, I got 130 megapascals. Like I was.
Yeah, that's fine. I would accept those.
Oh, okay, perfect.
Yeah, no, I would accept those. It's based off your eyes, right? Your eyes could be better or worse than mine, so that's a fair range.
Perfect. And sorry, just one last question.
Yep.
For problem statement, can we go to part C?
Part C. Sorry, part C of
problem statement 1.
Yeah. Okay.
Yes. Could you just re-explain the whole SN plot thing?
Yes. So I'll do that very quickly. So
thank you.
If I have if it works. Okay. So the way SN plots work, the mean stress increases as we go toward the bottom left corner. Okay. So up here we will find our sigma m of 0, and here we can find our sigma m of infinity, right? So if we know that this general trend occurs, we can sketch our 2 mean stresses first in the descending order. So 5 would be on top, and then the greater value would be underneath.
Yes.
After you do that, then it's just a matter of plotting your stress amplitudes. So the way I was explaining is you either start with your lowest stress amplitude, or you start with your highest stress amplitude and work down or work up. So in this case, we started with A because it was the highest. So we went to 400 and we went directly across to the corresponding mean stress. And then we went straight down. And then the next one was the 350. Again, lower than 400, so we went across and straight down. And the final one was 345, so it's very close to 350, but still below. We went across to the other mean stress, which is 5, and we went straight down.
Perfect. So the first step is the mean stress, and then after the mean stress, we go from the highest amplitude to the lowest amplitude.
Yes, absolutely.
Okay, got it.
Okay.
Yep.
All right. So I guess at this point I can say, are there any other questions about quiz 2 before we move on? Somebody's crying. Stop crying. It's too early to cry. Okay. Are there any other problems or questions about, where am I going here? About quiz number 2? No?
I had a question, but not related to the quiz.
Okay.
It's related to the problems of chapter 9. I was wondering if we can talk about that.
In terms of the practice problems?
Yeah, it's problem 9.26. I don't know if we can talk about that.
9.26. Did you send me an email about that one?
I don't think so, no.
No? Okay. Send me an email about it. I'll try to explain to you there, just because we have a lot to do still.
Perfect. Okay.
Okay. Thank you.
Yep, no worries.
All right. So I'm going to say we're good with quiz 2. So now we need, somebody had a question about the tutorial problems regarding.
Yeah, it was the tutorial 2 composite. It's under tutorial 2, but
I just hope I can find it here. There we go. Okay, which problem was it?
it's number 5.
Okay.
Okay, I just had a question based on this problem, like is specific stiffness and you said there's like a thing in the video that said specific stiffness has no units, and then you gave units to it. So I was really confused because you had this thing just like sitting on the screen saying no units, but then you just like put units on it. So
yeah. So when I was solving this problem, I was I thought the specific gravity was density, so I was putting the units for density.
Yeah, that's my other question. What like I don't know. I was just
I
confused.
wasn't gonna
I never seen this equation either in my life, so I was confused.
So this is just the rule of mixture equation. So as I was saying, the rule of mixture equation, you can use it for a variety of properties. So in this case, we used it for Young's modulus, and we also used it for specific gravity. So specific gravity is unitless. I thought it was a density when I was solving, so I was putting the units for density. So that's why I put that note saying that the specific gravity is unitless, not specific stiffness. If I wrote specific stiffness is unitless, then I got to go edit the video again.
It could be me just reading it and I read specific stiffness, but I mean, yeah, I read that one of them specific something was unitless, and I was just like, that does not make sense. But that makes more sense. And then for part B, all we did is that you just take it for each part and then you add them up in total, correct? It's just because in part in approach 1, all we're doing is we're doing each the composite in total, and and then for part B we just adding them together right away.
Yes. So this is actually goes back to what Michael did earlier. He did part B approach. He did approach 2. He did the calculation, then multiplied by the volume fraction.
Okay. All right, that's good. Thank you.
No problem. All right. So I'm assuming nobody's learned anything about magnetic materials, considering only like 10 people saw the video. However, it is on your midterm. So I don't know what you prefer, if we go through the quiz or we go through the tutorial problems, or we just go right to midterm review. I don't know. You all have to decide.
We haven't even learned magnetic in lecture yet, so maybe that's going to be today or tomorrow.
And we haven't even learned half of composites either.
Yeah, we haven't even learned like all composites.
We just like cram everything together.
We could try, but if you don't know, if you barely knew the composite equations, I doubt you'll know what the variables are for magnetic materials. But
no, we're not gonna know anything. I'm telling you right now.
We have 40 minutes, so we could do a lot if we go quickly.
I mean, I think there's a lot of suggestions in the chat that we should go over past midterms so we can prepare.
Okay, so you want to do the past midterms then?
Correct.
Correct.
Oh my goodness, there's 8 problems for magnetic. That's a lot.
Yeah, it's a lot. Okay, so let's do the past midterm. the calculation questions, the ones that you want, because we can't do them all. So we'll go through the selected ones. And then there are 2 magnetic material ones in there, so we can just do those quickly at the end. So let's open 2019 then, because I think that one was more challenging. If I was ready to do this.
It was more challenging, like a lot more challenging than the 2016 one. I see you laughing, so I'm assuming that you also know that that was a lot more challenging.
No, because I remember sitting there in the midterm last year and everybody's hands were going up. And it's not because the questions were hard, it's because she just presented them in a different way. And everybody was getting confused. It was so funny. But I know that if I was sitting there writing the exam in your shoes, I'd be so confused as well. So it's just ironic when you're in a different standpoint. But okay, let's do, I think somebody wants to do 2016 question 8. Okay, let's do that one first, and then we'll do the 2019 questions. I have to open this. I'm not sure which one this is. This is 2016. Okay, question 8. Which is question 8. Okay. Oh, this was very similar to the one that I did in the tutorial, no? Okay, let me not open the solutions because I feel like if I open the solutions, you'll just look at those and you'll get even more confused. So let me just solve it. Okay, number 8. So an aircraft wing component fabricated from an aluminum alloy with a plane strain fracture toughness of 36.4 KSI per root inch, fabricated at a stress of 53 KSI when the maximum internal crack length was 0.1. If the maximum internal crack length for the same component and alloy are 0.16 inches, compute the stress level at which failure will occur. Consider a safety factor of 1.5. What is the appropriate design stress for such a component? Okay, so what's the question asking us first off? I'd solved a very similar problem. It's just different units. So maybe that's why you're all a little confused. So you're given the plane strain fracture toughness, right? Which is what? What's the plane strain fracture toughness? Okay, I know what the value is. What's the unit? Sorry, K1C. What's the variable, I should say? So 36.4, that's KSI per root inch. Okay, so we have the plane strain, and we know that it fractured at a stress of 53. So our fracture stress is equal to 53 KSI. Okay, are we good so far? And we know that it had an internal crack length of 0.1. So we don't want internal, we want, what do we want? A over 2, which is correct. So we're going to say our crack length is equal to 0.1 inch divided by 2. Okay? So half an inch. Okay? Are we good so far? 0.05, yes. That's what I said in my head. I just didn't write it. Okay, good catch. Okay, so now it says if the maximum internal crack length for the same component of the alloy is this, compute the stress level at which failure will occur. So now we're saying if the crack length of the component is this value instead, calculate the stress at which failure will occur, right? So now we need to know, so this is our condition 1, and our second condition is if our crack length is equal to 0.16 inches divided by 2, which is equal to 0.8 inches. Okay? We good so far? Okay. So what are we missing? We'll ignore the safety factor right now. What are we missing? Yes.
Sorry, isn't it 0.08 again? Not 0.8.
Yes. 16 divided by 2. No, Is it 8 or 0.8?
0.08.
Yeah, I think it's
Yes.
0.08. Yeah.
Yes. Good catch. Okay. So what's missing from the first one?
Safety factor.
Safety factor. Okay. Missing one other thing as well. Our geometry factor, right? Where's our y? So the only thing that we have to relate the two components is our geometry factor, correct? It's the same component. So the first thing we need to do is solve for our geometry factor. And with that, then we can relate it to the second component or the second test. Okay, so let's solve for our geometry factor first. So our geometry factor is equal to K1C divided by the critical stress times the root of pi a, right?
What exactly is the geometry factor affected by? Like if you change the material, would that factor change? Like what is it affected by?
The geometry factor is exactly that. It's the geometry of the component. Okay, so for the quiz question, I gave you a contact lens. That geometry was a hemispherical shell. In this case, we're dealing with an aircraft wing. So this Y is governing the aircraft wing shape. Okay, it's a geometry of the component.
Okay, thank you.
Does that make sense or no?
If you change the material, would it change?
No.
No.
If you change the material of the component, the geometry factor will stay the same because it's only a factor of the geometry of the component. If you change the material, the plane strain fracture toughness will change.
So only if you change the size or shape of the component, the geometry factor will change.
If you only change the size and shape of the component, yes, that is correct.
Oh, okay. Thank you.
Okay. So let's plug in our values. 36.4 KSI per root inch divided by our critical stress, which is 53 KSI times the root of pi. And we said our crack length is 0.05. So what are we going to get? Anybody? So as long as the material is the same, y doesn't change. No, y has no effect, has nothing to do with the material. It's solely a parameter of geometry. 3 something, 42? No. Lol, 1.73, yes, 1.73 is correct. Okay, so now that we have our geometry factor, now what? So now we have our geometry factor, which we know is the same because it's the same component geometry. Okay. What do we know about the fracture toughness? Is it the same or is it going to change, the plane strain fracture toughness? It's going to stay the same, right? Okay. Now we're solving for our critical stress because we've changed our crack length. So can we solve? We can say that our stress is equal to geometry factor times the root of pi a divided by K1C. Do we agree? Oops, the other way around. Divided by y, pi a. Why does it stay the same? Why does what stay the same? The geometry factor or K1C? So we're still dealing with the plane strain condition, right? So we're saying both tests were done on the plane strain fracture toughness. It's just now we're changing the crack length to see what the fracture strength is going to be. Okay.
So as long as the plane stays the same, it doesn't change?
Yes, as long as we're testing under plane strain conditions, it's going to stay the same.
All right, thank you.
Okay. We have to divide sigma c by a safety factor, right? Not right now. We'll do it at the end. Okay. Okay, so let's plug in our values. 36.4 KSI per root inch divided by our geometry factor, which is 1.73 times the root of pi, and our new crack length is 0.08. So that's going to give us a critical stress of 41.9 KSI. Okay, everybody's following me so far? I hope I didn't lose anybody. Okay, so now the question says, consider a safety factor of 1.5. What is an appropriate design stress for this component? So right now we have our critical stress, right? So if we divide our critical stress by our safety factor, what are we doing? We're lowering the stress at which we're telling people to use it at to ensure that failure doesn't occur, correct? Yes. So we can say that our design stress is equal to our critical stress. I think we should label this as critical stress 2 and that one as 1, just to decipher between the two. And we'll divide by a safety factor. So we'll get 41.9 KSI divided by our safety factor, which was what in the problem? 1.5. And we're going to get a value of 27.9 KSI. Okay? Does everybody understand the problem now? It's very similar to the one that I did in the tutorial. The only difference is we're solving for a stress, not a new fracture toughness.
Nello,
Yes.
it makes sense. I just have a question. Should we always divide by the safety factor? I think I asked you this last week.
Yeah, so I was getting a lot of emails about this. So when you're using a safety factor, you have to think back to what you want to happen. So I got an email regarding a safety factor when we're using the fatigue limit. So the fatigue limit is a limit at which at that limit or below it will have infinite amount of cycles to failure. So if we multiply by a safety factor, we're increasing the stress. And if we increase the stress, we no longer have the fatigue limit, we have a fatigue life, meaning that we're going to have, fatigue strength, meaning that we're going to have a specified number of cycles to failure, which doesn't make sense intuitively, right? You want the component not to fail, so why would you increase the stress and make it fail? In this case, we're doing the same thing. We know that the component's going to fail with, we know that the critical stress on this component is going to be 41.9. So if we don't want the component to fail, we're going to make sure that the people use this particular component at a lower stress value. So we want to lower our critical stress by dividing by the safety factor to ensure failure is prolonged.
Okay. It makes it's confusing sometimes of what to do because I originally did it the other way around. I multiplied.
Yeah, just think back to what the problem's asking for.
Okay. So we use it at like the stress for the design. So like what that essentially means, right, is like what you said. So we're designing the material to have a stress of, or I guess a maximum stress in this case of 27.9. So that way, like I think you said this last time, but that way if they go over that, it still won't fail because like the real maximum stress is like 41.
Yes, that is 100% correct.
Okay, hopefully I can remember that for the test.
Yeah, that's 100% correct what you just said. Okay. Are we also expected to know imperial units for the midterm or final? Because I've rarely worked with them before. Yes, you're an engineer. You are in Canada, meaning we use both units. So you should know both. Okay.
Can I ask a question about the fatigue cycle?
Yes.
It's just like in general, like what's the difference between the tensile stress and then the maximum stress? Because there's yield stress, maximum stress, and then tensile stress on the cycle. It's just like I can't understand the difference between max stress and tensile stress.
There's max stress, tensile stress.
And
you have to show me what you're looking at. I can't visualize that. Is there a problem that uses it?
No, it's part of notes. It's like it's under like low cycle fatigue.
I don't have her notes, Professor Zari's notes, if that's what you're referring to.
Yeah, okay. Can I send you an email then?
Yes, please send me an email so I can look at it. Thank you. And I'll answer you as soon as I can. Okay? Okay, thanks. I'll try to learn them in 3 days. What's 3 days? Oh, the units?
Yellow. Try to learn for the midterm.
Yeah. Yes. Yeah, about the midterm. No, you're gone.
Oh, I was just replying to your question because you said 3 days for what? I said the midterm.
Oh, midterm. Yeah. Yeah. There's nothing you can do with the units. I'm sorry. If she's feeling really nice, she'll only give you SI units. Okay. Anything else from the 2016 in terms of problems? I did this one in the tutorial. That one's easy. This is all the same problem. This was very similar to the one actually that I did in the tutorial as well.
Hello. I think in the chat asked about, yeah, it was Karim. The very last question, I think, with the like cutting the fibers up into pieces.
Cutting the fibers up into pieces.
Yeah, I
This
know.
one?
Interesting. No, the one after that. Yeah.
Oh, this one. So now we're doing discontinuous.
Yes. I figured this question out, but my method was slightly different than what they did. So I guess as you go through it, I'll ask you a question.
Okay, so do you want me to do this? Does everybody want me to solve this question?
Karim was asking. I don't know.
Everybody's asking? Okay, I can do it. No problem. Okay. The design of a fiber reinforced composite requires 15% aligned and continuous fibers by volume to meet the strength requirement. The continuous fibers were 25 times longer than the critical fiber length. You are asked to redesign the component using discontinuous and aligned fibers. You decide to use the same fiber and matrix material as the original design, where the strength in the matrix at fiber failure is 0.01 times the strength of the fibers. To get discontinuous fibers, you decide to chop up the continuous fibers into smaller segments. If the maximum feasible volume fraction of the discontinuous aligned fibers are 25%, what is the maximum number of segments each continuous fiber can be chopped into so that your newly designed composite has the same strength as the original component? Note, please do not forget to check whether you have used the correct formula. Okay, so let me get firsthand what you think the problem's asking for.
I think it was the number of fibers it could be cut into.
Okay.
That's probably the first thing it's asking for, but it's what they're asking for in the end.
Yes. Okay. So when I showed you the table of equations for the discontinuous, right? There were two different equations governed by what? There were two equations.
L greater or less than LC.
Yes. Okay. So the first thing we need to do is figure out which one we're going to use. Okay. So somebody wrote max number of segments each fiber can be chopped into to achieve the same strength. Oh, okay, you just answered my question. Okay. So based off of this problem, what do we have to do first? We're going to assume what? Let me get my pen to work. The length is greater than the critical length. Why?
– 25 times bigger. L is less than 25 LC.
Yes. Okay. So if they're 25 times bigger, what can we say? What's our equation?
L is equal to 25 LC. That's what's in the chart.
Let me see.
That's the equation that you're looking for though.
No, that's not what I'm looking for. I'm looking for what can we say? We can say that 0.15, right, times the strength at fiber failure plus 0.85 times 0.01 strength of the fiber failure is equal to 0.25 x times strength at fiber failure plus 0.75 times 0.01 times the strength at fiber failure. So what equation is this?
This is the critical length stress.
Yes.
I didn't do it like that, but
Okay, how did you do it?
the way I used the same equation, but I didn't do the x's part of it. which
Oh, you
was-
didn't solve for x, so you plugged in the critical length right away, right?
Yeah, like I made the critical length in terms of sigma f star, and then I took that and then I equated that to then like the critical length of the discontinuous one, and then I crossed out all the sigma f stars because they were all the same.
Yep.
And then I solved for that ratio there that you just wrote.
Okay.
Then I got like that ratio, and then I divided 25 by the ratio that you got. Because it was like in the end, like I ended up getting that for the cut up fibers, it was like L is equal to 1.26 LC. So like for every one L, there was like 1.26 LC. So I just divided and I got 19, and 19 was the answer. So I was like, okay, I guess I did it somewhat right.
Yeah, so the what you explained, I think you did it slightly different, but I think it still worked out because all you did was substitute. You didn't solve for x, you solved directly for LC over L, correct?
Yeah.
Yeah, so that's fine too.
Okay.
The reason why she did it like this in the solutions was just, I guess, to simplify it, solve for x and then go back in and solve for LC over L. But if you want to manipulate the equation to solve for LC over L right off the beginning, that's perfectly fine. It'll just be a little bit harder in terms of manipulation of the equation, but it should be absolutely correct.
Okay. So I guess it was because it was still the same procedure. I just didn't do that. Okay.
Yeah, that's fine. Does everybody know what we're doing though, in terms of how we're attempting to solve this problem? Do we know why we wrote down this equation? Not sure. Okay. So what's the general equation? Somebody want to read it out to me? No? Okay.
You want me to read it out?
Yeah, if you can. If not, I'll go find it.
Okay, hold on. I think I have it here on the formula sheet.
Okay.
Sigma star CL
Yep.
is equal to sigma m prime times 1 minus VF plus sigma star F times VF.
Okay. So the problem said what? We want to make sure that the strength on the original component and the design is the same, right? So if we know that this is number one and number two that has to have the same strength CL, wait, this isn't the right equation. No, that's not the right equation.
What? Why?
Is it?
Yeah, I think.
Let me just check something.
What was the right equation then?
Where is it? This is the one that I wanted. If I can find it here.
Kyle wrote in the chat VM equals 1 minus VF. Is that what
This
you're
is the one I want. Sorry. This one here.
don't we need both of those though?
Yes, we need both.
Okay. Oh, sorry.
Oh, so sorry, you were giving me the first one. Not the second one. Okay. My apologies. Yes, we need both of these equations, and then we'll make them equal because the problem said that it wants the same stress or same
Yeah.
stress. Correct? Okay, so yes, you are not wrong. I misunderstood. I'm losing my voice. Where was this problem? Okay. So this one is not this. This is CT. And that's going to be the other equation, which I just showed, which is, somebody want to read it out to me? It's V,
It's sigma F star times VF
times VF.
times 1 minus LC
Yeah.
over 2L
Yes, that's it.
plus sigma M prime times 1 minus VF.
Sorry, sigma
Sigma
M
M
prime
times
times,
1 minus VF.
yes, that's the equation I was looking for. Okay, so when we set these two equal, as the problem says, then we can solve for our LC over L ratio. Okay? That's what I was trying to get at. And that's exactly what you did. You did it all in one step like this. What the solutions did, they just said, let's make this parameter equal X, solve for X, and then substitute back.
Yes.
Okay?
I did.
Do you understand what's happening, or did I just confuse a whole bunch of people by not knowing what the equation was? Can you re-explain how we knew that the new fibers will be greater than LC? That was, I believe, given. Let me see. So we assumed that first, right? Because what happens if we were to use the other equation? No, it was not given. That was an assumption you had to make. So how do you check that our assumption was correct? What are you going to do?
This was the part that I didn't understand. So
Okay. So the first thing we did is we assumed the condition that L was greater than LC. You could have assumed the other one as well. And then you would have got to the end and realized what? That your inequality didn't hold, correct? In this case, he gave you the note here saying, please do not forget to check if you've used the correct formula. Meaning after you solve the problem, check to see that your inequality holds.
oh, because there's two formulas.
Yes, there's two formulas and there's two inequalities. So that's what Michael's asking. How do we know? Well, the question is you have to make an assumption, right? You could have done both, solved both, and then realized one of the inequalities didn't hold, and then you would went back and did the other one. In this case, in terms of the solutions that Professor Zari posted, she already knew the answer. So she said, assume this, but you could have assumed the other one as well. Okay?
I thought we were saying something about how it was due to the 25 times longer than the critical fiber length in like the second sentence.
The continuous fibers were 25 times longer than the critical fiber length in the continuous and aligned fiber. But upon chopping them up, right, into a discontinuous.
We don't know. Oh, okay.
Yes. So I said yes to you originally, but I changed my answer. I'm sorry. Okay. All right. I hope I didn't confuse anybody. This was a pretty tricky problem, I will say. I would have been stuck. But it's actually a really good problem. Okay. So now what? Do you want to move on to any other questions from 2016 or 2019?
Nello,
Yes.
ask you a quick. Sorry, can I ask you a question?
Yes.
Just about the same question that we just did, the cutting one.
Yes, absolutely.
Yeah. So at the end, how would we? I guess it's in the solutions. I just don't have it in front of me. But
Okay.
how do we check that R length is greater than the critical length again? How do we?
So we know that, hold on. We know that the problem said it's 25 LC, right, is equal to the length, right? 25 times greater. If we divide that by the number of segments we just did, what are we going to get? We're going to get L over LC is equal to 1.3.
Oh, this is what I did. Yeah.
Meaning that L is greater than LC, right?
Oh, because it's greater than.
Yes, the critical length.
Because like 1.3 times the critical length is equal to. Okay.
Okay.
This is how I solved it.
Yeah.
Okay. There's a question in the chat now too. How do we know the two stresses are equal?
The problem says that. So the problem act says, what is the maximum number of segments each continuous fiber can be chopped into so that our newly designed component has the same strength as the original component. So that's how we know we need to set them equal. Okay? No problem. All right, so are we good with this problem? Yes? I don't know how many of you have class at 11 or not, but
We have this class.
you have this class at 11?
Yes.
Okay.
3 hours straight.
So that being said, we have 4 minutes. So what do you want to do in 4 minutes?
Just cry.
Okay, let me point out the tricks in the 2019 exam. And then you can solve them on your own time once you know the tricks, okay? This one right here. If I can get my pencil, know that the energy lost per unit volume is just the area inside this, okay? Inside the hysteresis curve. Okay, that's for magnetic materials. The reason I'm saying know this is because I know Professor Azari stressed it in lecture last year, but I actually didn't cover it in the tutorials. Not because I neglected to, just because I didn't know that it would actually come up. It came up, but it was covered in the lecture. So the majority of them that went to the lecture knew, the ones that didn't, oh well. So that was one trick question. Another trick question was this one. So this was, I was saying last week, the force amplitude is modeled by a particular equation. So if the force amplitude is modeled by an equation, we know that we can substitute our values and get a force amplitude. And once we have a force amplitude, we can use our stress is equal to force over area to get our stress amplitude. And then from our stress amplitude, we can get our cycles to failure if we know the mean stress. Okay, the mean stress was also given because it says a continuous load was a tensile load was applied at 8.2 kilonewtons. So with that, we can get our mean stress, sketch our curve, go and get our cycles to failure. The key point being here was part C. Part D, would the fatigue be longer or shorter if we eliminate the constant force? That was the schematic that we sketched in tutorial quiz number 2. Knowing that the mean stress increases in this direction, if we eliminate the mean stress, meaning it's a mean stress of 0, we know that our force amplitude is generally going to go up to the left, right? So we're going to have a longer cycles to failure. Okay, so that was the trick on this question. There was 2 tricks. One, the force amplitude was modeled as an equation. And the second being that if we eliminate the mean stress, will our cycles to failure increase or decrease based off of this and the schematic that we know it will increase. Okay. Another trick on this was here. Professor Azari expected you to know what we discussed earlier, which we referred to or called, if I can sketch, the isostrain condition, meaning that the strain in the fiber is the same as the strain in the composite, and therefore we are able to solve for the fiber failure. Okay. Again, make sure you label this as the onset of failure, clearly showing stage number 1 and stage number 2. And the final problem, I think, was on magnetic materials. You'll notice that in the tutorial problems and in the problems in the textbook, they give you N as a value and they give you L as a value. So the number of turns of the coil and the length of the coil are given separately. In this problem, she gave you the turns per meter, meaning she gave you N over L. So everybody was freaking out saying that they did not have a value for length and this problem was not able to be solved, which is false because she just presented the information differently, but everything you needed was given to you. Okay? And as you can see, it's very trivial. It's plug and chug after that. All right? And that's it. So those are the major tricks that I found in the exam. Everything else was very, very straightforward. Okay? Are we good? Are there any other questions? No? Question 8, 2019. Okay, what about question 8? Is it about the stress concentration factor? Can you tell me what you're confused about on this problem? All you have to do is explain and label these and label the curves, right? So you know that the stress concentration factor is equal to D over D, right? Or it's a function of D over D. Not equal to, I should say. It's a function of. So as D over D increases, the stress concentration factor is going to increase as well, right? Because they're proportional. Yes. So because they're directly proportional, then you're able to actually label the curve accordingly. Okay? Okay. Anything else? I'll take that as a no. Okay, so let me stop recording.